All right, so our last example is written on the screen. And this time we're going to work over a closed surface. So S is going to be the boundary of this solid E. And I'm going to assume S, by the way, S has positive orientation, meaning the normal vectors we want to shoot outward, not inward. And it's going to be the solid region E that's enclosed by the paraboloid 1 minus x squared minus y squared, and then the plane Z equals 0. So I went ahead and drew this for you. Here's the paraboloid. You shift up 1, and then you open down. And the plane Z equals 0, of course, is just the xy plane. So that's the floor. And so our surface is actually two pieces. Our surface S is actually the paraboloid, which we'll think of as surface 1, and then the bottom here, which we'll think of as surface 2. We said we want to have positive orientation, so we're shooting out. And let's dive into this thing. So first off, just to be clear, what you would want to happen, what you'd want to be able to do here is what you should do. So the surface integral over S of f dot ds, you can break this up as a sum of two surface integrals, 1 over S1 plus the other one over S2. And that's really nice. We can work out each one of these separately. So let's dive into the first one. So we'll work on S1. So let's just go ahead and say on S1, and we're interested in, first off, parameterizing this thing. And so we can see that we want S1 to have upward orientation. And when I think about the equation for S1, I say, oh, wait a minute, my equation, the defining equation for S1 is actually z equals some g of x, y. So I can use that parameterization like this. I can say r of xy equals x, y, and then 1 minus x squared minus y squared. So that's my parameterization. I want to think carefully about what x, y values is this parameterization good for. And you can see, well, if you extend this paraboloid down into z equals 0, you get exactly the unit circle. So this is on, let's just say, on the unit circle, and we'll come back to that when we set up our integral. So I want to write down my normal vector in, well, actually, yeah, so usually when I write in, I think of it as unit normal, so I won't write down in, but rx cross, I'm getting tired, ry, we know is going to be, well, it's negative g partial x. This is my g. So I get a negative 2x, and negative 2x gives me a 2x, and the negative g partial y gives me a 2y, and then I always have a 1 sitting there. And so just check now, this is your normal vector, and its z component is positive, so it is pointing up, and that's what we want. If we're going to have this surface, is everything has positive orientation, means all the normal vectors are pointing out from the surface, and that's what we want in this case. Up means out, so that's good. We've got the right orientation. If we didn't, not a big deal. We'd just slap a negative on that thing, and it would work out. And so now we're more or less ready to write down the surface integral over S1 of f dot ds1. This becomes a double integral over, let's just call the unit circle d, so over d of, okay, you take your parameterization and you plug it into f. Maybe we should go back and think about what f was. F is yxz, so let's write that down up here where we can see it. So here my vector field f is yxz. And so now I'm going to plug in my parameterization, so I'm plugging this r of xy into f. So everywhere I see a y, I put a y. Everywhere I see an x, I put an x. And everywhere I see a z, I put this guy. So I'm going to get y and x, nothing changes, and then I'm going to get 1 minus x squared minus y squared. Okay, and then I'm going to dot with r partial x cross r partial y. So I'm going to dot with 2x, 2y, 1, and then I'll end with a dA. And so at this point, we'll take the dot product, and we're going to get the double integral over the unit circle d of what? We're going to get a 2xy plus a 2xy plus a 1 minus x squared minus y squared. Now I'm going to realize, hey, I'm working over the unit circle. This is my region D. And so I'm going to switch this thing to polar. Let's combine these two as well. You know what? I'm just going to erase those and just combine that as 4xy. There we go. And we'll slide this over. Plus 1. And then let's see. When we switch to polar now, we can write this as what? R goes from 0 to 1. Theta goes from 0 to 2 pi. I get a 4r squared cosine theta sine theta. That's just coming from the 4xy, right? X is r cosine theta, y is r sine theta, so I get this. Then I get a plus 1 minus r squared, all times r, don't forget the r, dr d theta. And I would invite you to pause the video and work this out yourself. Push that r through, and you'll come up with pi halves. So that's the value of the surface integral on just S1. Now we've got to do it again and work it out on S2. And so I went ahead and wrote that down for us. And so we need to think really carefully about this. So S2 in this case is this plane, and we want this thing to be oriented. We said we want the full surface S to be oriented positively, which means everything is pointing out, which means the normal vector on this plane is actually pointing down. Now, please realize I want a unit normal vector that's pointing straight down, and that's just going to be just n equals k in this case. K here is 0, 0. Oh, I'm sorry, I said k. That would point up. I want minus k. 0, 0, negative 1 is going to point straight down in the z direction. And so the point is this: you can write this integral as the integral over S2 of f dot your normal vector in ds. And I don't actually have to plug in parameterizations. I can if I want to, but I want you to realize that when I'm on this plane, the parameterization is just z equals 0. So let's plug it in, right? The parameterization that I'm going to use here is r of x and y is x is x, y is y, z is 0. And so if I plug that into my f, I'm going to get the double integral over the unit circle d again. And I'm going to have what? Just y, x, and then z is 0, dot with the unit, the negative unit vector in the k direction, so 0, 0, minus 1 dA. And the point is z is 0. When I take the dot product, this 0 kills that, and these zeros knock this out, and so I end up with just the double integral over d of 0 dA, which is just 0. And so here I didn't actually compute my normal vector in the usual way. I didn't, for example, say, okay, this n. If you think about my n, we usually think about our surface and we parameterize it, and we say, okay, n is r partial x cross r partial y divided by length, whatever. In this case, I could see n is constant. This is a constant normal vector, unit normal vector, and it's just minus k. And so I can use that here. And then my parameterization is just z equals 0. So everywhere you see a z in f, you plug in 0, and things work out quite nicely. So that's that. We've finished with 13.7, and we will call it a day.